Okay, so here, let's take a look at here some graphs. We're going to introduce some more terminology here, right? So from as previously stated, right, we're going to be focusing on simple graphs here, and that means that the connections between the edges they're not directed, right? So v to x. So example, if you look at for example, if you look at the graph in front of us here, right, the edge from v to x is the same x to v, right? So they have the relation is symmetric, right? We don't need to distinguish the order of which way it goes. Sometimes it will be necessary to model certain situations, but here we'll start off where they're not directed, right? It's just a symmetric relationship, right? Think of like handshakes, right? If you shake a hand with somebody, right, you have shaken that hand, right? The other person does not need to like shake your hand again to establish that relationship. And we defined this idea of adjacent vertices. They're connected by an edge, right? And this idea of an incident edge is really just the incident where it's connected to a vertex, right? So here, V and this edge, Vx, the incident is where they meet, all right? Now, this allows us to kind of establish a definition of the degree of a vertex, right? So the degree of a vertex is referring to how many edges are coming out of that vertex. So for example, here, using this notation, the degree of u is 2, right? Because if we look at u, this is my vertex, there are 2 edges coming out of it, right? And again, here, we establish that we can define a graph by defining a set of v vertices, and a set E, which is the edges, right? All the edges that make up our graph. Okay, so from here, we want to introduce some other terminology here, and we're going to introduce this idea of something called a subgraph. So looking at this here, so this is our definition from our textbook, and let's read the first part. We'll just look at the first part, and then we'll move on to the second part here. So let's define subgraph, right? So there's really 2 types here, right? So the first type is we say that G prime is equal to V prime E prime is a subgraph of our graph G is VE, and right, G prime is a subset of G, provided V prime is a subset of V and E prime is a subset of E. All right, so just very general, right? This notion of subsets we've covered in a previous module, right? So here, if I call this my graph G that we see here, I can call this a subgraph here. All right, where V prime is U, W, Z, Y, and X. All right, it is a subset of V, and E prime is U, Z, Z, W, Y, X. All right, the subset of these not order, just pairs, right? And E prime is a subset of E. All right, so this is indeed a subgraph. But notice here I have a note, this is not an induced subgraph. Now let's go back to our, excuse me, right? Okay, so here we go. Here we see our subgraph, right? V prime being U, W, Z, Y, X, which is a subset of V, and E prime being the edges U, Z, Z, W, and Y, X, which you see is also a subset of E. Okay, so that makes it a subgraph, right? It satisfies that definition. Now, I have a note here. It says not an induced subgraph. All right, now let's see why that's the case, right? So let's switch over again to the definition. Okay, and here it states, we say that G prime is equal to V prime E prime is an induced subgraph of our graph G equals VE, provided V prime is a subset of V. And so here's an additional description. Every edge in E whose vertices are still in V prime is also an edge in E prime. Okay, so let's take a look here. All right. So looking at this here, right? So this is not an induced subgraph, and the reason being is because of these vertices y and x. While they are in V, right? What is not in E prime are all the vertices that are emanating from y and x, right? If it is to be an induced subgraph, then if my subgraph is going to include yx, it needs to include every edge, every incident edge of y and x. So everything coming out from y and x. Most notably here, yv and vx are not part of my subgraph, hence making it not an induced subgraph. Now what we can do to make it induced is if we look at something like this. Now this is an induced subgraph, right? So V prime is a subset of V, right? But not only that, right? If the edge UZ, UW, and ZW, all of those are the only edges corresponding to vertices UW and V. Excuse me, UW and Z. So now we have a proper induced subgraph. Okay? Since referring back here to our definition, right? Every edge in E whose vertices are still in V prime is also an edge in E prime, right? So every single edge in E whose vertices are still in V prime. So looking at V prime, U, W, Z, and then going to my graph here, all the vertices that have U, W, and Z. Right, those are also part of my E prime, which they are here. So now I have a proper induced subgraph. Okay, now also this is not a subgraph. Right, so it looks similar to the graph we had before, but one thing we have to watch out for is that if I can't just introduce new edges, right? In particular here, the edge UY is not an element in E, right? So it is not a subgraph, right? It's its own graph, but not a subgraph of my graph G that I have here. Okay, so that's the idea behind something being a subgraph and an induced subgraph. Now, the next thing here is this idea of a connected graph. So connected graph means that you can get from any vertex to any other vertex by following some path edges here. So looking at our example again, G, right? Now this is not connected, right? Mainly because if you're in, let's say, for example, right, there's more than one vertex, but if you look at vertex Z, there is no way to going along the edges to get to X. Okay? Now if I look at the subgraph UWZ, right, now this one is connected, right? Any vertex can get me to any other vertex by going along any of the edges here. Okay? All right. So that's the idea of connected. Now again, here there's no restriction on how many times I can pass an edge or do it that I need to wind up at the place that I started with. Those are all very specific types of paths that we'll talk about later. But for now, this idea of connected simply means that if I start in one vertex in the graph, I can get to any other vertex in the graph. All right. So now the next idea here is this idea of a complete graph. All right, so a complete graph is where we add all possible edges edges. All right, and that would make it a complete graph. So what I mean by that is, for example, here, let's say I had a graph with 4 vertices. Okay. All right. So if I graph here with 4 vertices, now I can think of this. This would be an example of a graph with 4 vertices. Right, but this is not all the possible edges that can happen here. All right. So what I mean by complete is that I essentially have an edge for each vertex going to all the other vertices here. So while this edge here in the corner goes to this one on the right and the one below it, I still need this one here. All right, and then from here, I need this edge here. All right, so now I've added all the possible edges. All right, so if I start off with one where I can see, all right, well, what are all the possible ones? This is what we will call complete. All right, where we have from one vertex all the possible edges leading to all the other vertices here. Okay. All right, now notice here that there's only one complete graph, right? Because we started off with 4 and then kind of like a rectangle shape, but really if we start off with a graph with 4 vertices, and maybe the graph initially looked like this. All right, not a complete graph, but if I start adding these edges to make it complete, well, I then wind up with that same graph that I have above. So essentially all roads lead to just the same exact complete graph. All right, and usually we define that to be with this capital letter K for, and then since there are 4 vertices, we call this K4. And in general, the complete graph with n vertices will be referred to as Kn. Okay? Now you might want to ask ourselves, well, how many, what would the degree be for each of these vertices? Okay. So the degree would be, if there are n vertices, well, I need an edge that connects to the other vertices, right? So notice here that for K4, each vertex had degree 3 because I need a path to go to the other 3 vertices. So in general, the degree here for a vertex of any vertex would be n minus 1, right? Now, if I want to figure out what is the total number of edges there, right? Now we can think of this as kind of that handshake problem, right? Where we might be tempted to just add up, well, if each of those has 3, right? Well, we just add up the 4 and each one of them has 3, so we have 12 handshakes. But again, we are double counting there, right? Because if I'm connecting one edge, the edge that connects these 2 vertices, I don't need to double count it, right? It's a symmetric relation, so going from one to the other, right, is the same as going, so actually let me just name it so to avoid confusion. Going from V1 to V2 is the same as V2 to V1. Right, so we can kind of think of this complete graph as the same thing as that handshake problem where the number of edges is n times n minus 1, but we have that. Right. And another way to think of this is we have n choose 2 edges. Right, if you're familiar with the choose number or the from our binomial theorem, if you've studied that previously. All right. Okay.